at all.
That's a good start. Oh, here we go. Yep.
That was slow. Hope that's not a sign. There we are. Hello, Fred.
Hello, Andrew.
We
Who
are.
are you again?
Pardon?
Who are you again?
Oh, I can't remember. That's a COVID side effect.
Yes, it is. Yeah. Tell me about
Oops,
it.
lost my headphone. For some reason, I can't keep these stupid earbuds in my ears. I've got two different types.
Yeah.
I've got these wacky looking things,
Whoa.
and I've got the AirPods.
Yes.
It doesn't matter what I put in there; they pop out. I've tried different size attachments and everything, but I just can't get them to stick.
There might be somebody inside pushing them out, Andrew.
I think I've got a small ear canal.
Yeah, actually, I do too. I have a real problem with earbuds for exactly that reason.
Yeah, because I was out putting something together for the backyard yesterday, and I kept having to catch them because every time I moved, out they'd come. So that could happen a few times.
Blue tack.
Blue tack inside your ear. Great idea. See, every time I smile, it squeezes out.
Yeah. You just have to keep a straight face.
No laughing today. No laughing allowed.
Okay, right.
Okay. All right. This is a test, by the way, and thank you for joining us if you've tuned in, because we are about to record episode 299, but we're doing a live test for episode 300 next week, which we will be able to give details about at last. Not everything we're going to do, but there'll be a few surprises, possibly.
There's a surprise this week as well. This COVID brain fog that I was just talking about has afflicted me again because I haven't got the Rode mic plugged in. So this is coming through the MacBook mic. So I hope it'll do for this week. Well,
it certainly sounded great last week. So
yeah, all right.
I think it'll be fine.
Next week I'll remember the Rode mic.
Yes, he's talking about one of these.
Yes, indeed. Yes,
that's a Rode mic.
A Rode mic. Rode.
It's a very good unit. That I love it.
Made in Australia.
I've got mine on a boom on the desk.
Oh,
yeah, see?
Look at
that. Oh, look, my tissues for all my COVID sneezes.
Yeah.
No, I haven't had it. Well, not that I'm aware of.
No.
Okay, we got to record the promo.
All right, here we go.
In 3, 2, 1. Hello, I'm Andrew Dunkley, the host of Space Nuts, and I hope you can join us every week on your favorite podcast distributor to talk astronomy and space science. And joining me, as always, is Professor Fred Watson. What's on this week's edition, Fred?
I like that. Yeah, we've got lots of good stuff. We have the discovery of a planet that's forming in a way that has not been seen before too much, and also an idea for putting together a huge spacecraft in space built in a kind of Lego fashion, which is great. Yeah.
That's fascinating. And I always thought making planets out of plasticine was a great idea. Join us on the next episode 299 of Space Nuts, out Thursday on your favorite podcast distributor. There you go.
Sorry, that threw me. I forgot we were doing that. Sorry.
That's okay.
No, it's the new style. It takes me a while to get used to these things.
Yes, well, we're doing the TikTok promos now because we had about 250 views last week on the.
That's pretty amazing. Yeah.
Which it is stunning. Seeing, I don't even look at TikTok as a rule, but I am addicted to Instagram Reels. Okay. I've had more than my fair share of stupid dog and funny cat videos. I think I've got a lifetime's worth. I don't know why I find it so entertaining. I think it's just to escape. It just keeps me focused on fun for a while.
That's good.
All right, I'm going to hit the. I'll just check and see if Hugh's message to say anything's happening. Okay. We're live on Facebook and YouTube. And he's still typing, so
okay.
I'll just give him a thumbs up because otherwise I'll keep looking at this and I'll get distracted like I did last time.
Yeah. Thumbs up.
All right, we will begin in 3, 2, 1, 0.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5.
Hang on, I botched. I'm supposed to do my intro before I play it.
All right.
Yeah, there's another blooper for next week.
Just fill it with bloopers, that's all.
Yeah, well, we haven't got many because we don't generally stop.
No.
But I had to then because it was the beginning. All right, here we go. In 3, 2, 1. Hello once again. Thanks for joining us. My name is Andrew Dunkley, the host of this here podcast called Space Nuts. Great to have your company. I hope you're well. Coming up on this edition, an unusual planet formation discovered. What's that mean? Well, this is a planet that's being born a very different way, it appears, and a spacecraft that's going to be built of Lego. Ish, could be, and much more. A couple of questions. Oh, look, a black hole question. How different? And we're going to talk about temperature and spacecraft that are exposed to the sun and how they protect them. That's all coming up on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
It's so good to have your company. Thanks for joining us on episode 299. We are one short of 300, but apparently we're all away next week, so we're not going to do it. And joining me, as always, to talk astronomy and space science is Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. How are you doing today?
I am well. What about you? How are you recovering from your exposure to the dreaded COVID-19?
Yeah, it's a slow process. I'm doing okay, feeling fine generally.
Yeah.
You're just aware that something's not quite right. A little bit of congestion, perhaps, and things of that sort. But no, I'm okay.
Everyone I've spoken to who's had it has reported some kind of different after effect. I've spoken to people who've just had a little bit of, baby brain, if I can call it that. They're just they can't stay focused. Energy, loss of energy is a big one. Persistent cough, just a little bit of heavy breathing type of stuff. None of that, nasty stuff on the phone, but just the with normal breathing, that kind of thing. Everyone's got a different story, which I find fascinating, but disturbing all at the same time. Okay, Fred, I'm glad you're on the mend. That's the good news.
I think so, yes.
Now, for those who are wondering what's going to happen with episode 300 next week, we have a plan, which I will tell you later, because we want to get to our first story. I'll just put that on the bottom of my run sheet so I don't forget. But an unusual planet formation has been discovered. Was this the one I heard about that was through Hubble?
Yes, it's a Hubble discovery.
Okay.
As these things often are, and it's one of these stories that doesn't exactly upend what we know already, but it certainly casts a new light on the way we think things work in space. So you and I have talked many times before, Andrew, about planet formation, and the standard method is something that's usually called the core accretion method. So what you get is bits and pieces sticking together, small objects, basically bits of dust to start with, that gradually stick together. That's what the accretion means. It's things sticking together and forming eventually solid lumps, and eventually those solid lumps come together to form what are called planetesimals, which might be a couple of 100 kilometers across. And then they too stick together to form protoplanets, which might be, the size of Mars or the size of the moon or something like that, which eventually collapse to form the core of planets. And I think in this specific case, Andrew, we're talking about gas giants, the likes of Jupiter, the big planets, how they're formed. So the core accretion method is the standard way that we think planets of this kind were formed. However, some new observations which have come from direct imaging taken with the Hubble Space Telescope, long may it continue, it's still doing fabulous work, that seems to be, and it's a protoplanet that's forming through a different method, which is being called disk instability. So core accretion is the normal one that we think we observe. Disk instability is what the researchers themselves describe as an intense and violent process, because core accretion is a fairly gentle process. There are collisions involved, things smash into each other and forms debris again, and then the debris re-sticks together. But generally speaking, the coming together of bits and pieces is relatively slow. It's as these objects come together under their own mutual gravity, and eventually, there's so many of them that they heat up, and that forms a kind of melting that allows the things to stick together. So it's not a violent process, whereas disk instability seems to be. So what are the observations about? Well, it's a planet around a star called AB Aurigae, which is in the constellation of Auriga the Charioteer, which is a Northern Hemisphere constellation. It's right above Orion in the Northern Hemisphere. Its brightest star is Capella, which is actually a sun-like star. But AB Aurigae is actually a variable star, which is why it's got that slightly peculiar name. And we can see a disk of protoplanetary material. So one of these protoplanetary disks, which we've talked about many times before, usually because of observations from the ALMA Atacama Large Millimeter Array. But as I said, these are Hubble observations. They've used a Space Telescope imaging spectrograph and their near-infrared camera and multi-object spectrograph. So these are two different instruments on Hubble that have been used. In fact, in connection too with instruments on the Subaru telescope, that's the 8.2 meter telescope operated by Japan at Mauna Kea in Hawaii. So this is the coming together of some of the world's great facilities, the Hubble and Subaru. And what's been observed is this disk. Now, we're very fortunate in this case because this protoplanetary disk is actually face on to our line of sight. So we can see it sort of almost in plan, Andrew, kind of mapped out for anybody to see. And what has been detected is structure in the protoplanetary disk, which includes one very bright part that is being interpreted because of the observations, the spectroscopic observations, as this process of this violent and what was it, the expression, an intense and violent process, a planet forming by disk instability. It appears as a bright spot in the images that we've seen. There is a lot of emphasis on exactly what is being seen here, because if you can observe over a long period, and they have done, which is actually one of the reasons why the Hubble telescope's been used for this. They've observed this thing with the Hubble over a period of 13 years. That allows you to see the orbital motion of this thing. So you can actually see this planet moving in its orbit over only a small distance because it's a long way from its parent star. It's about 3 times as far away as Neptune is from the sun. So it's way out in the depths of its solar system. But the motion has nevertheless been detected. And this process that's going on has also been detected spectroscopically. So it's an exciting result.
Yeah, it's also something we've caught in the early stages of solar system formation. I mean, you compare the age of our solar system to what's been discovered,
yes,
and
that's right.
it's quite young, 2 million years old, they reckon.
Yeah, compared with 4.57 billion years for our solar system. So we are talking about two very different, epochs or periods in planet formation. But
I suppose people would find it surprising that planet formation is still sort of in early phases in some parts of the universe. But I guess if the universe continues to expand, there are always going to be, well, not always because it's all going to end one day, but there's going to be these processes happening at different stages.
Yes, that's the great thing about astronomy. We look out into space and we can see all these phenomena happening at different phases. It's why we know so much about the way stars evolve, Andrew, because we can observe stars at different phases in their lifetimes, from the youngest to the oldest, and indeed even beyond the grave we can see them because we can see black holes.
Yes.
So it's a really it's one of the one of the attributes of astronomy, that you can look at many different objects, and we can see all these different phenomena. And planetary formation, of course, is one of the hot topics in astronomy at the moment. So it's very much in the forefront of the research field. Looking at the way planets form, and this is a very nice story that comes directly into that into that arena.
Now, you said because of the angle, we can actually see it sort of side on. Someone's going to ask why that's possible, given everything sort of spreads out on a plane in the universe, or does it?
Well, not really, no. So things, we see things at different angles. Galaxies come at different angles, which is why some of those we see face on, some we see edge on, some we see in between. It's a mishmash, and the same. So this is an object in our galaxy, and we're observing it just at exactly the right angle to see the disk face on, and that will be the case for a few million years yet. So we're not going to lose that that angle that it presents to us. Not for a while, anyway.
Okay, we're saying this one's 2 million years old. When will it be at a point where it's, I don't know, a normal solar system?
That's a great question, and it's once again that's the subject of debate. How long does planet formation take? And the current thinking is that it's a pretty rapid process, that the planets, if you look at our own solar system, for example, as I said, 4.57 billion years old, but we think that the planets as we know them today would have been formed within the first 100 or 200 million years of that time. That it's a really early, a really rapid process at the start of a solar system's life. Gets all the nitty-gritty ironed out. There would have been, we know that there was a phase probably 500 million years later, maybe 600 million years later, where everything was charging around and everything was colliding into everything else. A period that we call the late heavy bombardment, and that late heavy bombardment also stirred things up a lot. What caused most of the craters on the moon, for example. But even then, it was relatively small chunks, leftover bits of debris that were charging around, not big protoplanets themselves.
Fascinating. I've just done a quick calculation, and
if
you're right, oh, I had to work it out. Probably wrong. My mathematics sucks. But if you're right about it taking about 200 million years for the solar system to form, we will be able to report on it on episode 10 billion of Space Nuts.
Okay. That's something to look forward to. Yes.
Yeah. Maybe. All right.
Are you
we'll
sure?
Leave it there.
Are you sure it's not episode minus 10 billion that we would be reporting on it? Because we would have a grandstand seat in front of all the action for that.
Yes, we would. Could be. That's a good thought, and also very confusing.
Yes.
This is Space Nuts with Andrew Dunkley and Fred Watson. Okay. So I might do the prelude to 300 now.
Okay, good.
So that gets out on all our platforms, because I have to do an abbreviated version of the show for the radio edition. So quite often the beginning of the third segment never gets heard by the radio audience.
I see.
Just the timing thing. Okay, let us carry on in 3. You all right?
Yep, all good.
Good. All right, in 3, 2, 1.
0G, and I feel fine.
Space Nuts.
Now, we have been building up to this for quite some time. So by next week, when we are live on all our podcast platforms with episode 300, you'll probably go, oh, is that all they're doing? And you're right. That's basically how it's going to go. But I will sort of furnish you with some thoughts about how we're going to tackle the live show next week. There will be bloopers. Somebody asked for bloopers. We had a live guest lined up, but he's gone on holidays. So we're looking at a possible replacement, but no guarantees there. We will be taking live questions via Facebook, probably. And we will also be doing some giveaways, and we'll have a game of skill required for that. And the time, most importantly, the time will be 10:30 p.m. Universal Time on Monday of next week. So that is Monday hang on, I didn't bring my calendar up.
The 11th.
Monday the 11th of April, 10:30 p.m. Universal Time. So you'll need to work out what Universal Time is in your locale or your local time zone to work out when we will be on air live. And the other thing I can't guarantee is that it will be exactly 10:30 p.m. Universal Time, because we tend to run late sometimes. So just stand by. We'll have, maybe we should get a piece of A4 paper with standby on it, stick it in front of the camera. I don't know, but that's the plan. So 10:30 Monday, Universal Time, 10:30 p.m. I should have done it in
22:30.
22:30. That's it. Yeah. So bear that in mind for next week, and for those on the east coast of Australia, that will be 9:30 a.m. Tuesday. For those who, that's the only one I can convert. Anyway, that's where we're at, and I hope we're right. Tune in an hour earlier just in case. Sit there and twiddle your thumbs, whatever it takes. Now, Fred, let's move on to our next story. And this one seems to have a lot of elements to it. But they're looking at building this massive space station. You suggested out of Lego, but not real Lego, probably.
No, it's not.
But are they also looking at artificial gravity in this experiment?
That's right. So that's what this is all about. It's how you can, transfer the idea of a spinning space station into reality to provide simulated gravity for its occupants. And of course, this all goes back decades. I'm sure many of our listeners will remember the rotating space station in 2001: A Space Odyssey, which was right on the money as to how you might do this. And it's an idea that's been studied in great detail. In fact, a few years ago, I had the pleasure of talking to a gentleman. It's actually Linda Spilker's husband. You remember Linda Spilker, who was the project scientist for Cassini?
Yes.
Her husband actually runs a company that looks at exactly this sort of phenomenon, the idea of providing artificial gravity. And I had some really interesting talks with him about the limits on how well this would work. And it turns out that what you've got is some sort of disk, and the humans are around the edge of it, or other objects that you want to put into artificial gravity. But it turns out that if you spin it at much more than about 3 revs per minute, then everybody gets sick, because it's just like in a washing machine. And so what you have to do is spin it at a slow speed, and the slow speed then dictates that you're talking about something big. You're not talking about a disk that's 20 feet across. Yeah. You're talking about something 1 kilometer across. So that you get the proper effect of gravity on scales that don't make you sick, basically. And so what this story is about is it's really just a progress report, I guess, on projects that are being looked at through the NASA Institute for Advanced Concepts, NIAC, and they basically issue grants to universities and things like that. And 2 of these grants have gone to teams at Carnegie Mellon University and the University of Washington for basically clever ideas about how you can build a kilometer scale space station, which will rotate and have artificial gravity.
Yeah.
Now, kilometer-long structures are not things that you can carry up easily on spacecraft unless you're very clever about the kind of technologies that you would use. And that's really what this is all about. It's the structures. And you're quite right, it's not Lego-like things. It's basically structures that fold up to be very, very compact.
More like a Meccano set.
Yeah, that sort of thing. That's right. If you, I mean, I remember making Meccano bits and pieces that.
Me too.
Usually,
I love that stuff.
Yeah, it was great. So that there is a technical term for the kind of thing that we're talking about, which is a high expansion ratio deployable structure, or a HERDS, HERDS, which is quite a nice. A nice acronym for this sort of thing. So what do you mean?
I hadn't heard of that.
No, I hadn't either. I hadn't heard of it. Thank you, Andrew. That's a very nice pun there that went right over my
It's not a very nice pun at all.
15 seconds.
Terrible.
There must be another one in there.
Look,
these
don't start me.
Herds of ideas come this way.
Oh dear, oh dear.
But the name tells you what.
Moving right along.
Yes, high expansion ratio deployable structure. So high expansion ratio means it's the ratio between what it's like when it's folded up and when it's not, and it's a very high ratio, and probably with numbers in the hundreds. So this thing gets hundreds of times bigger when you press the button and it is deployed. That's the deployable structure bit, and so. There's actually a really nice piece which I think was originally on Universe Today. I saw it on SciTech Daily, which has got some videos of some of these structures being used or being deployed. Where you basically you press a button or release something and it springs into action. It's a bit like. I guess a nice way to think of it is when you press the button on an umbrella that opens up on its own.
Yeah.
You click the button and suddenly it's gone from a long stick into something that's going to keep the rain off you. And that's very appropriate as I speak because it's pouring down again here in Sydney.
Oh, gosh.
Once again, the gutters are overflowing. Anyway, never mind all that. If we were outside, it would be very nice to have an umbrella in this weather. And that's basically, I guess, a HERDS. An example of a HERDS, high expansion ratio deployable structure. Whoops, sorry. Yeah. So, and I think this is really promising. I love the idea of creating large space stations. I've kind of rambled on about this before because, if you want to colonize space, the way to do it is by building these large artificial structures. You provide your own gravity, and you essentially allow the engineering to dictate where you're going, rather than the fact that you've got a nice Earth-like planet next door, similar to Earth next door, for example, Mars. Which is why I don't think we should be colonizing Mars. I think we should be building HERDS in space. There you go.
Yes, fair enough. I did see an interesting science fiction solution to the artificial gravity problem in the TV series The Expanse, which I thoroughly enjoyed. Okay. What a great show. Yep. The special effects are amazing, but they didn't have artificial gravity on most of their spacecraft. But they did have electromagnetic boots.
Okay.
and the floors were all made of metal. So you just turned the boots on and you could walk around.
Yeah. I think,
I think the problem with that is if you're in space long enough, the muscle wastage would eventually make it more and more difficult for you to walk with magnetic boots. That's the only problem I can see with it.
So when we were in COVID lockdown last week, we explored the extremes of what's available on TV, on the web.
Yeah.
And I picked out one because I wanted to pick out one of my favorites. And so we wound up with Wallace and Gromit, Andrew. And I don't know whether you remember, but one of the episodes of Wallace and Gromit is called The Wrong Trousers, and it's got exactly what you're talking about there, except they weren't magnetic. They were vacuum operated, a bit like flies' feet, I guess.
Oh, right.
Suckers on the bottom of your trousers, allowing you to walk along ceilings and things of that sort. I'm sure
there's such clever stuff there. Well, the latest science fiction series that I've attached myself to, because I used to play the game with the boys when they were young, is Halo.
Yeah, well, Halo's the classic example of a rotating structure.
Yes,
It's
and
brilliant.
the critics have been pretty nasty with the TV series of Halo,
Yeah, I didn't
and a
know
lot
that.
of the purists are saying, but I'm just taking it on face value. I'm loving it. I'm really loving it, and the special effects are magnificent.
That sounds great.
So but yeah, I can relate to the characters because they're all straight out of the game.
Yes.
There's a couple in there. The only thing that disappointed me is when the very first edition of the Halo game, when it came out, started with a movie role introducing us to the Master Chief, but also the spaceship, the battle cruiser he was on, called the Pillar of Autumn. I loved the names of things in it. The Pillar of Autumn. It was a great name. But they didn't start it that way. They started on this planet we'd never heard of with these characters that we never heard of. So maybe that put people off initially. Mm-hmm. And guess what they were mining on this planet? You'll never get it.
Wouldn't be cheese, would it?
No, deuterium.
Deuterium.
Yeah. I don't know what they wanted to use it for.
They
never explained that, but it was a highly sought after commodity. Possibly. Yeah. Yeah. Anyway, and I'm also interested to see that China is very keen on this experiment. They're obviously keen to get artificial gravity solved as well. I guess anybody who's going into space would like to solve it.
Yeah, that's right.
Okay. We'll leave it there for the moment. But if you want to chase that story up, it's on scitechdaily.com. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
And I know we're live, but I'm just going to leave you for 2 seconds.
All by myself? What am I going to do?
All by myself. Just hang on a second.
It's not like I do this in radio. Oh, dear. I could do a tour of the house. That'd be, there's not much to see. In fact, it's pouring rain where Sydney is, but we've got absolutely perfect weather at the moment, mid-20s Celsius, sunny. Actually, I can show you my neighbour's house. That's about all I can do. Through the fence. Can you see that? They're the solar panels. Good time of year for those because we've got the sun in the north. Yeah, that's about all I can show you. The cable won't go very far. I bet I've not centered that either. No. Oh, dear. There we go. I'll see if Hugh's messaged us in the meantime. Yes, he has. Facebook viewers are starting to find out we're live. Well, I kind of figured you would. I don't know how many, but thank you for watching.
Sorry about that.
This is a test.
I just I saw Marnie put her head through the door while we were talking, and I wondered if there was a panic.
Right.
And there isn't. No, not really.
Okay. All right. You ready to continue? We've got 2 questions. We've got 3 from 2 people.
Sounds good.
All right.
More than merry.
In 3, 2, 1.
Space Nuts.
And if you would like to become a patron of Space Nuts, you can do so by logging onto our website and look at the options. There are all sorts of ways of supporting us financially, or just by buying us a cup of coffee, which you can do on our website, spacenutspodcast.com or spacenuts.io, or you can leave a review on whichever podcast platform you use. Reviews are very, very helpful. They just help to spread the word. Apparently, the more reviews, the higher up the chain we go in the scheme of things, and more people can find us. So those are options. But yeah, thanks to the patrons. I haven't looked on the patron list lately, but the numbers have jumped. So thank you very, very much for joining us as patrons. We really, really do appreciate it. Now, Fred, let's get into some questions. This one's a very quick question from Simon.
Hello, Fred and Andrew. This is Simon here from Sweden again. If gravity has an infinite reach, would that mean that all that exists would eventually end up in a single black hole? Thanks. Keep it up.
Oh, that was quick, but it's a deep question.
It is very profound.
Yeah.
So what balances gravity is motion, and that's why black holes don't just sit there and suck up everything, because we know from observations in our own galaxy that there are stars in orbit around the black hole at the center of our galaxy. We can see them moving around, and they're at no risk at all of being sucked in by it. So as long as you've got things moving around and everything moves, then there's not going to be a situation where a black hole will suck everything in. Plus the fact that, as you and I have spoken about many times, the expansion of the universe is accelerating. So everything is, if you think of a single random black hole somewhere, on the larger scale, things are moving away from it because they've been carried away by the expansion of the universe. So I think the answer is no. The entire contents of the universe will not ever be sucked in by a black hole. But Simon's right. Gravity is one of those forces that basically has infinite reach. It reduces by the inverse square law. When you go twice as far away, it reduces by a factor of 4. But nevertheless, it at some level, it's always there. So, but it's not ever going to be a situation where it will, the gravity of a single black hole will suck everything into it.
Well, I think we've talked about the end of the universe before, and early theories were the Gnab-Gib, the big crush, which is the reverse of black hole Big Bang. But the latest, theory is, is that it will just continue to expand, and there could be a big rip, or we'll just move so far away from each other, we'll all just eventually just be cold, dead rocks in space.
That's right.
And that's going to happen. That's going to happen next week, just before we're about to start episode 300. Darn it! That'll solve a lot of problems, huh?
The big rip would solve a few, wouldn't it?
Yeah, it probably would. Yeah, but if there was a big rip, let's say it happened right now, how quickly would we know about it?
So the big rip is when space-time itself gets torn apart, and before that happens, the atoms have been torn apart. So we're already, we're already curtains.
But we don't have to worry about that either. We
don't have to worry about the big rip. That's right.
That's good.
That's good news, yeah.
Yes. All right. Thank you, Simon, for your question. Great to hear from you. Let's now get a couple of questions from Ralph.
Hello, Top Nuts. This is Ralph in Northern California again. A couple quick questions. I'm sitting here in the warm California sun. It feels great on my neck and back, and I'm thinking, gosh, when our planet revolves to the other side and I don't get the direct energy from our nearby star, it gets much cooler, of course, and even cold at times up here. And I'm thinking, is that the same when you get above the atmosphere? It's out away from the greenhouse effect. Do you still get a very hot energy effect from direct sunlight? And then when you're behind an object in the shade, does it get cold, like, that super cold of the vacuum of space, etc.? Just curious, because that means we'd probably never find life anywhere else if it didn't have an atmosphere, if that's the case. Second question is related to the recent pictures of the sun. They look so great. It's amazing. How do they protect the spacecraft when they, the craft that's getting so close to the sun? I'm sorry, I can't remember the name at the moment. How do they actually protect that thing from being cooked? Interesting stuff. Thanks as always. Great show. Bye.
Aluminum foil. Aluminum foil, sorry. Got to talk American sometimes on this show. No, I don't know. But good questions. That first one about temperature is interesting. Of course, we're on the other side of the planet, and aside from all the dirt from the north falling on top of us as a consequence of that, we're going into the cooler months. So we're having the opposite. We're having little cold snaps and things like that at the moment. And then we sort of rebound into some warmer weather, and then it drops again. So you're having the opposite happen. But the effect of, on a hot sunny day, walking under a tree and feeling cooler is also something that happens on a planet-wide scale, isn't it, Fred?
Yes, that's right. So, Ralph, he's hit the nail on the head, really. in that to feel the sun's heat, you've got to have something that feels it. And in the case of the Earth, it's both the atmosphere, which is heated by the sun's radiation, and the surface, which also gets heated by the sun's radiation. But I think Ralph's assessment that to have living organisms, you need an atmosphere is probably about right as well, because what the atmosphere does is it regulates the temperature on the surface of the planet. If you think of the moon, which is devoid of an atmosphere or any atmosphere to speak of, it's got something called an exosphere, which is a few atoms per cubic meter, but not enough to make any difference to the heat of that you'd feel on you were there. It's the surface of the moon itself that when it's on the daylight side, it gets very hot. I can't remember the exact numbers, but it's something in the region of 150 degrees Celsius. It might even be a bit higher.
Wow, really?
On the surface, yeah. And on the night side, it drops to a similar number below zero. It's 130 or 170, something, I can't remember the exact figures, but it's of that order. There's something like a 300 degrees Celsius range of temperatures, and it's because there's no atmosphere there. So on the day side, the sun is warming up the surface with this incessant heat, and the surface temperature goes up. On the night side, all that heat's being radiated out into space because there's nothing to stop it. There's no blanket of air that actually prevents that. And the same's true of spacecraft. If you've got a spacecraft up there, it's got a day side and a night side, and the designers of spacecraft have got to think very carefully about the thermal balance, about how you balance this heat, heat influx on one side and heat loss by radiation on the other. And so there's a lot of clever engineering goes into those spacecraft to allow that to happen.
Yeah, I remember when it was at Skylab had a bit of a problem, and they had to create a shield. They made some kind of umbrella. Was that Skylab?
It might have been, yeah. I think that's right. Going back to those days.
Yeah, I remember that.
Yeah.
I didn't realize the temperatures got so high on the moon. How did the astronauts cope?
They so all the lunar landings were in. I mean, remember the daytime on the moon.
They chose temperate zones.
Well, yes. So the daytime lasts for 14 days. The sun's above the horizon for 14 days on the moon, and what they did was they landed early in the solar day, so the sun was still relatively low and not heating the surface up to these incredible levels. And you're right, it depends on where you are. They were in relatively temperate zones, but it was choosing the early morning moon time, which kept the temperatures controllable. And of course, they had heat insulating boots and all the rest of it to stop their feet burning.
Yeah, fascinating. So that sort of answers the question about temperature.
Yeah.
But the sun observing spacecraft, and we were talking about one last week that's actually been grazing the outer atmosphere of the sun.
That's right.
How does it not get destroyed? What's protecting it?
That's right. So I think what Ralph's talking about is the Parkour solar probe, which was the first spacecraft to fly into the solar corona, the sun's outer atmosphere, and quite low into it as well. Now, I've got the Wikipedia page open in front of me for the Parkour solar probe.
Wiki.
Good old wiki, yeah. The incident solar radiation that it feels when it's nearest to the sun is, here you go, 650 kilowatts per square meter. Now, if you think of, you think of a one kilowatt heater, which we all used to have, and you're a meter away from it, you know what heat comes of that. This is 650 of those per square meter of surface area, which is about 475 times the sun's intensity at Earth orbit. So it is really hammering down onto the spacecraft, but it's fitted with a heat shield. It's hexagonal. It's made of a reinforced carbon-carbon composite, and can withstand temperatures outside of about 1370 degrees Celsius, or 2,500 degrees Fahrenheit, with a white alumina reflective surface to minimize the absorption. And when you think about it, Andrew, that's not that surprising, because when a spacecraft re-enters into the Earth's atmosphere from orbit, it's got a heat shield that's withstanding similar temperatures to that. And that's just the standard, like on the space shuttle, on the Apollo spacecraft, the SpaceX Crew Dragon spacecraft, they've all got these heat shields that can withstand these very high temperatures. So it's not that surprising that you can do it with a spacecraft that is flying next to the sun.
Yeah. Okay. And those tiles that they used on the space shuttles, you can heat them up and immediately put your hand on them and feel nothing.
Radiate the heat away.
They're amazing. Yeah, I've actually held one. My son's got one. He got it from a fellow who used to work for NASA, who sent it to him as a Secret Santa on the Reddit platform.
Whoa, that's fantastic.
It came with a warning: do not leak. Apparently, it's got some pretty nasty stuff in it.
It probably has. Yeah.
But this was a discarded one. There was something wrong with it, so they couldn't use it in the program. So it just sort of got put on the discard pile. They have a pile of bricks out the back of NASA, all black and white. I don't know. But it was fascinating. He's still got that at home somewhere. But and so very light.
Yeah.
It's like picking up styrofoam. Yeah, quite incredible. Thank you, Ralph. Hope we answered all of your questions. Appreciate that. And if you have any questions for us, don't forget to send them in. You can do that on our website via the Send Us Your Voice Message tab on the right-hand side, or you can click on the AMA tab up the top and send us a text question or a voice message. We are happy either way. Love to hear your voices, though. Don't forget to tell us who you are. And, of course, keep those questions coming in and we'll use them in future episodes. Not so sure we'll be using them next week because it's a live program. And you can catch us live from 22:30 Monday Universal Time, which is when we're planning to do the live show. So that's Monday, 10:30 p.m. Universal Time for the 300th episode of Space Nuts, where we'll be going live. We're hoping to have a live guest. I've put the question out. He's thinking about it.
Oh, is he?
Can't tell you who it is. We're going to have some giveaways. We're going to take some live questions from you, the audience, on our Facebook page, probably. So on the Space Nuts podcast group page, we'll let you know on the day, and it will hopefully go swimmingly. Today we've actually tested a live program on several platforms, and I'll find out soon whether or not that worked. But initial suggestions are yes, we have audience right now live. So thanks for watching.
Yeah.
So that's the plan for next week. So we'll put some more announcements on Facebook so that you know what's going on, and that way we'll all be able to join up on Monday of next week. Universal Time 10:30, which for Eastern Standard Time listeners in Australia will be Tuesday morning 9:30, because we're on the other side of the international date line, which is always confusing. Why do we have to do that? Anyway, that's the plan. Fred, as always, thank you so much. 299 down.
No, it's hard to believe, isn't it? How did we
get
here, Andrew?
I don't know.
Anyway,
lots of patience, blood, sweat, and tears, and COVID.
That's right. And a lot of people who seem to like what we do, which staggers me no end. But it's fabulous.
I think it's great, fabulous. All right, thanks, Fred. We'll catch you next week, and looking forward to number 300.
Sounds good.
See you then. Fred Watson, astronomer at large, part of the team here at Space Nuts, and of course Hugh back in the studio, who does everything that we don't, which is, well, nothing really, but we thank him anyway. Thanks, Hugh. We look forward to your company next week, episode 300 of Space Nuts. Until then, bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.
Thanks for watching the live feed. We'll catch you next week.
Sounds good.
Bye.